After studying this module, you shall be able to understand clearly 1. The direct methods of estimating demand function, specification of the empirical demand function, linear and non-linear empirical demand function, method to estimate the parameters, forecasting methods, linear trend forecasting technique, forecasting in the presence of seasonal variation, and lastly use of dummy variables to correct seasonal variations. In the previous chapter, we learned about the importance of information of demand on consumer side. Information about demand is also essential for making production and pricing decisions. Companies like Nokia, Apple, Samsung and many other mobile handset companies use empirical estimates of demand in making decisions regarding the different kinds of models, about their price, the quantity to be produced, the advertising campaign in order to target the right consumers, expansion plans among many other decisions. Big corporations use empirical demand functions and econometric price forecasts while taking price decisions, as it is really important to set an optimal price. Changing prices is a costly affair. Hence, producers and their managers try to avoid the possible mistakes made during the price decisions. Statistical forecasting does not fully eliminate the uncertainty prevailing with the pricing decisions, but nevertheless it definitely provides better insights, thus helping in better pricing decisions. These decisions require statistical demand analysis and forecasting using advanced software packages along with judgment and qualitative analysis of the information. The fundamental integrant of this statistical analysis is the empirical demand estimation. These demand estimations are derived from the data actually obtained from the market. In this chapter, we will discuss methods of demand estimation. Firstly, the direct method, and secondly, by using regression analysis. We would also look at the time series methods of forecasting future prices. This method can be used for a wide variety of forecasting needs of a business. Methods of demand estimation. There are direct techniques of demand estimation that do not involve regression analysis. These methods are quite sophisticated and require expertise in order to estimate demand accurately. They include A. Market experiments and B. Consumer interviews. This section discusses these methods in brief along with their pros and cons. Let us look at market experiments. This is quite an expensive and somewhat difficult technique of estimating demand functions. This method attempts to hold everything constant during the study or experiment except the price of the good. There are laboratory experiments as well as field experiments, wherein the former volunteers are used to simulate actual buying conditions, and in the latter firms display their products in different showrooms at different locations with different characteristics and population over a period of time and observe consumers' behavior and choices. Experiments performed in the laboratory are a compromise between market study and market survey. In these lab experiments, firms look for suitable volunteers and pay them to simulate actual buying conditions, but without going through the real markets. They are given an experience of an actual shopping trip and experimenter changes relative prices between trips. With numerous shopping trips by various consumers, an approximation of demand is obtained. Volunteers have the choice and hence probability of retaining their purchases. Hence, they have an incentive to act as if they are shopping for real. In the second method, that is field experiments or field study, when firms display their products in the actual markets, they make certain that there are enough units available at the showroom at each price in order to satisfy demand. Hence, there is no impact of change in supply. The researchers want to change the price of goods and actually observe the behavior of the consumers. So, during the experiment, the price is slowly changed with small increments and record of sales is made at each price. With this, it is possible to remove influence of other things and a realistic approximation of the actual demand is made possible. Consumer interviews. Another direct method of estimating a demand function is through interactions with the consumers. This straightforward method simply involves asking the potential buyers how much of the good they would buy at different prices. This method involves various techniques, from a simple interaction with the consumers by stopping them and asking them how much they would buy at various price levels, to a more sophisticated method of developing a detailed questionnaire to a selected sample of the population. The interviewer has to be careful while selecting the right representative sample. This sample should have the same characteristic as the population itself. A random selection of members from the population has to be made. This means that if the male-female ratio in the population is 60 to 40, then the sample should also have the same ratio approximately. In real life, it is difficult to get a perfect sample and true representation of the population. Hence, if the sample is biased, it can lead to biased and misleading results. The sample would consist of relatively well-off people and it would be upwardly biased and will not represent the true population, where most population is middle class. Another problem is that there can be a response bias, where the response given by the interviewee to a question is different from his or her actual action he performs when she is actually facing the situation. Yet another problem is that the interviewee is unable to answer accurately. If they give people in the sample a list of prices with small increments and ask them the change in the quantity demand, there is a possibility that the consumers are not able to visualize the change in their demand quantity until they face the actual situation. However, though the method has some problems, it is still a very valuable method to know the actual needs of the people and quantify the demand on the basis of their responses. Care has to be taken while selecting the sample and framing the questions posed to the consumers in order to minimize the distortions. Let us look at the functional form of empirical demand function. We need to specify the functional form of the demand function. It can have both a linear or a non-linear form, and both will be discussed below. Considering the determinants of the demand of a good X, that is its own price Px, income M, the prices of the related goods, that is Pr, taste and preferences T, and the number of buyers B, a general demand function can be written as X is equal to function of Px, M, Pr, T and B. The function requires careful specification of all the factors. For example, we need to define the physical boundaries of the market in which the product is to be sold. If a firm sells its product only in India, then M should measure the buyer's income in India in rupee terms and not in dollar terms. Similarly, we need to look at the available substitutes and should include their prices because they affect the sales of the product. Also, researchers sometimes include a population measure as a proxy for the number of buyers. Hence, overall careful consideration is required while collecting information for estimating the demand function. Linear empirical demand function. A linear demand function is specified as X is equal to alpha plus beta in Px plus gamma M plus delta Pr plus lambda B. For practical purposes, we choose to ignore the variable of taste and preferences T, as it is difficult to quantify tastes of a consumer. In this equation, beta measures the change in the quantity demanded that would result from 1 unit change in price. We assume it to be negative, which we will discuss in unit 2. Also, gamma measures the changes in the quantity demanded where there is 1 unit change in income M. It is positive or negative for a normal or inferior good. Similarly, delta measures the change in the quantity demanded with 1 unit change in the price of related good. The related good can be a substitute or a complement. If the related good is a substitute or complement, then the relation would be positive or negative. Lambda measures the change in the quantity demanded with 1 unit change in the number of buyers. This linear equation is estimated by using linear regression techniques, and significance of the parameters are checked using t-tests or examining p values. We can calculate various elasticities using these parameters, as these parameters give the slope, and if we multiply the slope with the relevant ratios, we get the measure of elasticity. This means price elasticity of demand is given by EP is equal to beta into Px by x. Similarly, income elasticity of demand is given by E1 is equal to gamma into M by x, and cross price elasticity is given by EPR is equal to delta into PR by x. Let us look at the non-linear empirical demand function. The most commonly used non-linear empirical demand function is a function in log linear form, which can be written as x is equal to alpha into px to the power of beta into m to the power of gamma into p r to the power of delta into b to the power of lambda. This functional form provides direct estimation of the elasticities. To obtain estimates, we convert this equation to linear in natural logarithms, which is as follows: log x is equal to log alpha plus beta log px plus gamma log m plus delta log pr plus lambda log b. This is equation number 6, where the value of the parameters measure relevant elasticities. That is, beta measures the price elasticity of demand, gamma measures the income elasticity of demand, and delta measures the cross price elasticity of demand. Selection of a demand specification. It is important to carefully choose the exact functional form between linear and non-linear, but unfortunately the researcher does not know the exact functional form of the demand function. An incorrect functional form, if used, can lead to biased estimates of the parameters. Final selection of the demand function is based on mainly judgment and experience. In some cases, the researcher runs multiple regressions to reach the most suitable functional form. He or she can check the validity of the functional form by observing the signs and significance of the parameters. If the signs are wrong or parameters are insignificant, then it can be concluded that the functional form is not correctly specified. The question is, which of the two linear and non-linear demand equations are more appropriate in different situations? If the data has a wide range of price and quantity observations, elasticity is more likely to vary. Hence, a linear demand function specification is more suitable. Whereas, if the sample is clustered around a narrow range of values, the log linear form is more appropriate. Estimating the parameters. A firm needs to set price for its product, and for that purposes, firm needs to estimate demand, which is done in the following steps. A. Specify the firm's demand function. This is done by choosing an exact functional form of the demand function as discussed in the previous section. B. Collection of data for all the variables in the demand function. After the demand function and related variables are clear, data is collected for all variables including the quantity of the good, its price and all the shift parameters. C. Estimating the firm's demand. Generally, linear regression method is used to estimate the parameters of the demand function, from which respective elasticities can be computed. We use an example of demand curve faced by a firm to illustrate the above methodology. An upcoming fast food delivery chain, Burger House, which delivers burgers in area Y and has one competitor in the neighborhood, namely Big Burger. The manager knows that the consumers are price and quality conscious and compare its prices with that of competitors' price. Hence, the manager decides to collect prices in the last 12 months of its own product as well as the price charged by the competitor. Also, the manager is able to get the average annual household income data. Then, the price and income data is deflated by using the price indices. Data for number of residents is collected from the local municipal office. It turns out that number of residents did not change in the last 12 months. So, the variable can be dropped from the specification. The following linear regression is estimated for following demand specification using the 12 months observations. X is equal to alpha plus beta Px plus gamma M plus delta PR, where X is equal to sales of burgers at the burger house, Px is equal to price of a burger at burger house, M is equal to average annual household income, and PR is equal to price of a burger at Big Burger. The least square regression gives the following results. Results of the regression. We will have 3 rows: variable, coefficient value and p-value. For variable Px, coefficient value is minus 115.09 and p-value is 0.0003. For M, coefficient value is 0.09 and p-value is 0.0005, and for PR, coefficient value is 10.23 and p-value is 0.0001. Intercept 1180.43 and p-value is 0.3890. All the 3 parameters are tested for statistical significance at 5% level of significance with the degree of freedom 9 into n minus k is equal to 12 minus 3. Elasticities are calculated at values of Px, M and PR that the manager feels typify the burger market for the last 12 months. The values are Px is equal to 9, M is equal to 20,000, PR is equal to 10. At this point, the value of X comes out to be X is equal to 1180.43 plus within bracket minus 115.09 into 9 plus 0.09 into 20,000 plus 10.23 into 10 is equal to 2047.54. The elasticities are calculated as follows. Price elasticity of demand is given by EP is equal to beta into Px by X, which is equal to within bracket minus 115.09 into 9 by 2047.54, which is equal to minus 0.505. Similarly, income elasticities of demand is given by EI is equal to gamma into M by X, which is equal to 0.09 into within bracket 20,000 divided by 2047.54, which is equal to 0.8 9. And cross price elasticity is given by EPR, which is equal to delta into PR by X, which is equal to 10.23 into within bracket 10 divided by 2047.54, which is equal to 0.05. X is equal to alpha plus beta Px plus gamma m plus delta PR. Here delta measures the change in sales of burgers at Burger House due to change in price of a burger at Big Burger. Correspondingly, the coefficient of cross price elasticity of 0.05 is to be interpreted as a 10% increase in price of Big Burger leads to a 0.5% increase in quantity demanded of burgers of Burger House. Forecasting. In this chapter, we will focus on the quantitative methods of forecasting. When the data is available, then statistical methods are used as they are more scientific and cost effective. Forecasting requires a time series model. Past data of the variable is used to forecast the future values. We confine our discussion to time series model. A time series is simply a time ordered sequence of observation on a variable. It describes the process by which past data is generated. Hence, we need to specify a mathematical model that explains the generating process. Linear trend forecasting. This is the simplest time series forecasting technique. We take an example of sales of a company and they want to predict whether it will rise or fall linearly over time. Suppose data for sales is given for the period 2000-2001 to 2011-12, that is 12 data points. The best fit model is calculated with the help of simple linear regression, and the fitted line indicates a positive trend. The firm can assume that the trend continues in the future and forecast the future sales by extending the line and extrapolating for the desired period, say 2013 to 14 to 2016-17. We can see this in the following diagram. The orange dashed line shows the extrapolated values for sales of the future period. We can generalize this linear relation between time and sales of the product X as follows. XT is equal to A plus BT, where XT is equal to total sales of the good in period T, T is equal to 2000-2001, 2001-2002, 2002-2003 up to 2011-12. We regress T, the independent variable, on X, the dependent variable, to obtain the estimated trade line. If the value of B is positive and significant, then we get an upward trend. If B is negative and significant, we get a downward sloping trend line, and if B is equal to 0, then sales are constant over time. This can be used to forecast the future values, that is X 2016-17 is equal to A hat plus B hat into 2016-17. Presence of cyclical variations or seasonal variation. Time series data may exhibit regular variation, and we need to account for this kind of variation as it would bias the forecast while estimating the forecasting equation. The regular variation that time series data exhibits is also known as cyclical or seasonal variation. Hence, we need to incorporate such variations while forecasting a trend. We will see below the method to handle such cyclical or seasonal variation. Use of dummy variables to correct seasonal variation. Dummy variables are independent variables which take the value of either 0 or 1. Just as a dummy is a stand-in for a real person, in quantitative analysis, a dummy variable is a numeric stand-in for a qualitative fact or a logical proposition. A relatively straightforward approach to modeling and forecasting seasonality is through the use of dummy variables in multiple regressions to represent the season. For any k categories, only k minus 1 dummy variables are needed to represent it in a regression. For example, we can represent quarterly time series with 3 dummy variables and monthly series by 11 dummy variables. The excluded quarter or month is known as the reference category. For example, the complete model for a monthly time series can be specified as follows. xt is equal to a0 plus a1t plus b1 m1 plus b2 m2 plus b3 m3 plus b4 m4 plus b5 m5 plus b6 m6 plus b7 m7 plus b8 m8 plus b9 m9 plus b10 m10 plus b11 m11, where a0 is the intercept, a1 is the coefficient of the time trend component, and b1, b2 up to b11 are the coefficients that indicate how much each month differs from the reference month. m1, m2, m11 are the dummy variables for the first 11 months, that is equal to 1 if the observation is from the specified month, say January, otherwise 0. xt is the monthly sales in 1000s. The value of dummy m1 takes a value of 1 if the sales are from the month of January and takes a value of 0 if any other month. Hence, xt represents the sales figures in the tth period. Using the data, we estimate the equation. xt is equal to a0 plus a1t plus bm. The specification produces two equations, one in which dummy is equal to 0 and one where dummy is equal to 1. The slope would be the same, but intercept would be different. For the month of January, the intercept would be a hat 0 plus b hat 1, and for the rest of the months, the intercept would be a hat 0. This says the sales would be x hat t is equal to a hat 0 plus b hat 1 t in the months of February to December, and it will be x hat t is equal to a hat 0 plus a hat 1 into t plus b hat 1 for the month of January. Perhaps the best way to explain the use of dummy variables can be used to account for seasonal variation is through an example. Let us take the example to use the dummy variable technique. The manager of a company producing heaters X wants to predict quarterly sales of their product X heaters for all the 4 quarters. It has trend over time and also is subject to seasonal variation. Hence, data is collected for the period 2010 to 13 to forecast the sales, taking into account the seasonal fluctuations in the next 2 years. The data has 16 observations. This requires estimating an equation containing 3 dummy variables, that is, one less than the number of periods in the cycle. The equation to be estimated is xt is equal to A0 plus A1t plus B1d1 plus B2d2 plus B3d3, where d1, d2 and d3 are dummy variables for quarter 1, 2 and 3 respectively. Using the data, the manager estimates the equation and gets the following results. This we can see in the form of table. Results of the regression with dummy variables. We have variable, coefficient value and p-values. For variable intercept, the coefficient value is 1599.1 and p-value is 0.0001. For T, the coefficient value is 271.34 and p-value is 0.0001. For D1, coefficient value is minus 700.59. P-value is 0.0001. For D2, the coefficient value is minus 658.21 and the p-value is 0.0001. For D3, the coefficient value is minus 672.22 and again the p-value is 0.0001. The results clearly show a positive and significant trend in sales as A hat 1 is greater than 0. The above low p values indicate that the prediction of the sales for next 2 years will be higher. The manager calculates the estimated intercepts of the trend line for each quarter. Let us see this in the form of a table. Again, we have intercept for different quarters, estimate for intercept and value of the intercept. For the first quarter, that is Q1, the estimate for intercept is A hat 0 plus B hat 1, whereas the value of the intercept is 1599.1 minus 700.59, which is equal to 898.51. For the second quarter, that is Q2, intercept is A hat 0 plus B hat 2 and the value of the intercept is 1599.1 minus 672.22, which is equal to 926.88. For the third quarter Q3, the estimate for intercept is A hat 0 plus B hat 3 and the value of the intercept is 1599.1 minus 658.21, which is equal to 940.89. The estimates indicate the sales for heaters are lower in the first 3 quarters. The manager checks for the significance of these intercepts, that is, if A hat 0 plus B hat are significantly lower than A hat 0, then it is necessary that B hat is significantly less than 0. So, a t-test is performed to check its significance. The intercepts in all the 3 quarters come out to be significant, which gives evidence that sales are significantly lower in the 3 quarters. We can see this by plotting the value in a graph. The next step is to forecast sales for first quarter of 2014, for which T is equal to 17, D1 is equal to 1, D2 is equal to 0 and D3 is equal to 0 also. Therefore, the forecast for sales for the first quarter of 2014 is X 2014 T is equal to 1599.1 plus 271.34 into 17 minus 700.59, which is equal to 5511.29. In the same way, we can predict for all the quarters. The linear trend model discussed above is one of the simplest models from among many different types of time series models that can be used to forecast economic variables. More advanced time series models require detailed discussion, which is not in the purview of this course. An advanced course on forecasting would teach how to implement more sophisticated time series modeling techniques. Activity: calculate the future sales for the above example for the second, third and fourth quarters of 2014. Compare the value and also compare them with the data values for the period 2010 to 2013. Let us summarize. Look at basic techniques of demand estimation and forecasting in the present chapter. There are 2 specifications for demand: linear and non-linear. When the demand is specified in the linear form, the coefficient measures the rate of change in the quantity demanded, holding all other explanatory variables constant. When the demand is specified in non-linear form, we convert it to log linear form and the coefficients measures the relevant elasticities. Time series forecasts use the time ordered sequence of historical observations on a variable to develop a model for predicting future values for that variable. When data exhibits seasonal variations, dummy variables can be added to the time series model to account for the seasonality. If there are n seasonal time periods, then n minus 1 dummies are to be added to the demand equation. Precaution to be taken: incorrect specifications of the demand equation can undermine the quality of the forecast. Also, further, is the future to be predicted, wider is the confidence interval and hence greater the uncertainty.